So we are almost at the last segment of this chapter. The portion that we are going to begin today is absolutely different from the things that we have already discussed. The topics today is electrolytes and electrolytic conductance. Remember, along with that, we are going to talk about some new terms like resistance, resistivity, conductance, conductivity, specific resistance, and obviously the molar conduction. So this is a completely new segment. Numericals are also different. So first of all, we need to be habituated with the definitions and the new terms. So let us do that one by one. So let us first talk about this topic known as electrolytic conduction. The basic theory is that whenever an electrolyte is dissociated, whenever the electrolyte is dissociated by applying current, of course, by applying current, what happens is, as a result, the electrolyte is able to conduct electricity. Anything related to that. This is the fact that electrolyte is able to conduct the electricity when we are applying the current through them. This phenomena is known as the electrolytic conduction. So regarding that, we have got few laws. One of the very famous law is known as Ohm's law. So we have got to know the related terms and obviously the Ohm's law. So let us start understanding Ohm's law. First thing first, Ohm's law. The law states that the current flowing through a conductor is directly proportional to the potential difference across. Let me write current flowing through the conductor is directly proportional to the potential difference across. Now, suppose for an example, the current is I and the potential difference is V. So, according to this law, V is proportional to I. Now, obviously, here I is the current and V is the potential difference. As a result, we should be able to write, if we were to remove this proportionality term, we all know, I think it is there in physics, you must have read, V is equal to IR, where R, so R is a constant, it's a constant, and it is known as the resistance of the conductor. So it is also regarded as the resistance of the conductor. So this is the scenario of Ohm's law. Now, R is expressed in ohms and is represented by this one. Check. And this is the symbol of R. Remember, it may be stated that the strength of current flowing through the conductor is directly proportional to the potential difference. And this we must understand at the same point of time that the higher will be the resistance, the lesser amount of current will be flowing through the conductors, electrolytic conductors. So now let us see few basic related terms which is commonly used in this particular case. So as I have mentioned that V is equal to IR, obviously if we further write, here you can write that I is equal to V by R. So it is quite obvious the greater will be the R, I will be lesser. And R, this one, is regarded as an obstruction of the current flowing through the circuit. So what we can see is that resistance is nothing but the measurement of the obstruction to the flow of current. Now let us see little bit more details about the resistance. So let me erase. Let us talk about resistance. Let us talk a little bit in details about the resistance. Now, as I have said already, it measures the obstruction to the flow of current. So you can write it measures the obstruction to the flow of current. As a matter of fact, it is observed the resistance which has been expressed by R, it is proportional to L. Obviously L is the length of the conductor. And it is inversely proportional to A, which is obviously the cross-sectional area of conductor. So if I combine both of these, I will be able to write down R is proportional to L by A. And to remove this term, it is written R is equal to rho into L by A, which is a new term for all of us. This one. Now this rho is known as the resistivity or specific. This rho that we have written is known as the resistivity. So let us write down specific resistance, also it is called this one, resistivity or resistance. Now, since we have mentioned what it is, so we should be remembering the fact that according to IUPAC suggests that it always recommends the use of the term resistivity over specific resistance. So I believe we will be using this term over the specific resistance. Now if I rewrite if I rewrite this fact, where R is already is equal to proportional to L by A, if I rewrite, so R is equal to rho into L by A. If I take L is equal to 1 centimeter, and if I take A is equal to 1 centimeter square, so it should be R is equal to rho into 1 by 1. So we are getting R is equal to rho. That means under this condition, the resistance is equal to resistivity. So if it is asked that what is resistivity, we should be defining the resistivity as, let us redefine the resistivity. We should be defining the resistivity as the resistance of a conductor. The resistance of a conductor having 1 centimeter length and 1 centimeter square cross-sectional area. So we should be writing it is the resistance of a conductor having 1 centimeter length and 1 centimeter square cross sectional area. So it is mathematically established. Now, as we have seen that the unit, if we are talking about unit, we know that rho is equal to, if we write from here, rho is equal to R into A by L. So rho, you can write R into A by L. So here we can write it is ohm into centimeter square divided by centimeter. So obviously it should be ohm centimeter. So that is how we can determine the unit. Now we will talk about conductance. So let me erase. Next topic is very famous conductance. So while writing what conductance is, let us first mention that it is a measure of the ease in which the current flows. I repeat, it is the measure of the ease with which the current flows. It is the measure of ease with which the current flows. Now, it is expressed as G. Remember, G is equal to 1 by R. The R we already know. So it is the unit of conductance at the reciprocal of ohm. That means we should be able to write the unit should be ohm inverse. Remember, R is the obstruction to the flow of current, and it is the measure of ease with which the current flows. So obviously these are almost just opposite to each other. Next, let us talk about conductivity. So let us talk about the next topic, which is conductivity. Remember, these terms are very much required in order to understand the electrolyte and its electrolytic conduction. So conductivity, it is just the inverse of resistivity. So it is inverse resistivity. So inverse of resistivity means, if we write, it is expressed in kappa, so it is 1 by rho. Now here, few things we have to say, that conductance of a solution of, it can be defined as the conductance of a solution of 1 centimeter length and having 1 square centimeter as the area of cross section. Because remember, what is resistivity? Resistivity is the resistance of a conductor of 1 centimeter length and 1 centimeter square cross sectional area. So this one is just the opposite. So it is the conductance, it is the conductance, very very important, it is the conductance of a solution of 1 centimeter kept in, obviously solution of 1 centimeter length and 1 centimeter square cross sectional area. It is just opposite. So obviously, if we are talking about its unit, we know it should be, this one is ohm centimeter, so it should be ohm inverse centimeter inverse, just opposite. So these are the things that we have got to know. Now let us talk about the next topic, which is the molar conductivity and molar conductance. Next, we are going to talk about the molar conductivity and molar conductance. So the heading is molar conductivity. Now, in order to write what molar conductivity is, we should be writing that it is the conducting power of all ions produced by dissolving 1 mole of an electrolyte. It is the conducting power of all the ions produced by dissolving 1 mole of an electrolyte in solution. So it is expressed, as you know, it is expressed as lambda n, and it is kappa by, kappa by C. This C is the molar concentration, remember. Kappa we already know, it is molar concentration. Now, further to say, when C is the molar concentration, as we have mentioned, now if C is the unit of molarity, that means the moles per liter. If C is expressed, suppose C is expressed in moles per liter, in that case, this lambda will be expressed as 1000 into kappa by C. And this particular formula we need to remember throughout this lecture. So it is only when, because we are going to face the problems like this in moles per liter. In that case, 1000, it will be multiplied by 1000. Now let us talk about the relationship between conductivity and molar conductivity. So here it is relationship between conductivity and molar conductivity. Now, the above relation can easily be obtained from the definition of the terms. Suppose we take, carefully listen, we take 1 centimeter cube solution and they are dipped into electrodes. Solution is kept into electrode which are 1 centimeter apart. And the cross-sectional area is 1 centimeter square. Now, what we can see is the measured conductance of the solution will be its conductivity. So, what we can say is from here is that, carefully see, once again, if you remember the terms, if the solution is placed between the electrodes having 1 square centimeter area of cross section lying 1 centimeter apart, so we can write the measured conductance of the solution will be its conductivity, because by definition it gives conductance of 1 centimeter cube solution. So what we can say is its measured conductance. Measured conductance for all of these. The measured conductance for all of these is equal to its conductivity. Right? Further, suppose that this solution contains 1 gram mole of an electrolyte. So we have to keep that in our mind. Suppose it contains 1 gram mole of an electrolyte. So we know here also, if the solution contains 1 gram mole of an electrolyte placed between two parallel electrodes of 1 square centimeter cross sectional area and 1 centimeter apart, so that is also the molar conductivity. If it is having 1 gram mole of an electrolyte, if we measure the conductivity, it should be molar conductivity also. So we should be writing that the conductance is equal to conductivity, which is kappa, is also is equal to molar conductivity, which is lambda. Now, what we are going to do is, carefully see, we are diluting the solution to 100 cc. Now what happens? If we are diluting this solution to 100 cc, so there are now 100 cubes of the solution. Gives 100 into 1 centimeter cube of solution. And conductance of each 1 centimeter cube will be conductivity, so that the conductance of the solution will be 100 times of its conductivity. We know this one is its conductivity. If we write separately, don't know whether it is visible or not. It should be its conductivity. Now, as a result, we erase this part. As a result, what we should write is that if it contains 1 gram mole of an electrolyte, the solution is diluted to 100 cc. So there are now 100 cubes of solution, as I have already mentioned. The conductance of each 1 gram of centimeter cube will be conductivity, so that the conductance of the solution will be 100 times of its conductivity. But now also the solution contains only 1 gram mole of an electrolyte. So the measured conductance will be also the molar conductivity. So here, only thing that is changing is if it is diluted to 100 cc, it is 100 into 1 centimeter cube of the solution. But still, the total solution contains only 1 gram mole of an electrolyte. So we should say that molar conductivity, because the total solution contains 1 gram mole, and we are measuring the conductance of that only, should be equal to 100 into conductivity. You can see here. What is that 100? It is the increased volume, increased V rather. So what we can say is, in words, it is actually lambda m is equal to kappa into, kappa because conductivity, into this V. What is that V? It is the increased volume which we have introduced. So it is becoming 100 times in this case. It may be something else also. So this is the desired relationship. Not only that, further to elongate, if we want to write, now if C is the concentration of the solutions in moles per liter, if C is the concentration of solution in moles per liter, then what we can say is, if it is having m moles per liter, if suppose it is m moles per liter, that kind of case, if it is m moles per liter, then we should write that m mole of electrolyte is present in, m mole of electrolyte is present in 1000 cc. So 1 mole of an electrolyte is present in 1000 by m cc. So thus what we can say is lambda m is equal to kappa into volume in centimeter cube, kappa into, carefully see, volume in centimeter cube containing 1 mole of electrolyte, containing 1 mole of an electrolyte. And this particular part, volume in centimeter cube containing 1 mole of an electrolyte, we have already measured. So from here only we can say that after erasing this, we should be able to write that this is from here only, that lambda m is equal to kappa into, here it is the addition, which is what we have calculated, 1000 by m. This particular equation or formula, whatever you say, will be utilized again and again, and its unit is Siemens centimeter square per mole. We are going to show it to you later how it is determined, but as of now this is the form and this is the unit. Furthermore, if we are talking about the calculation of conductivity, so we have already seen few equations, that is, suppose kappa is equal to 1 by rho. We have already seen that rho is equal to, R is equal to rho into L by A. So these two equations or formulas we have already seen. Now from here only we can write that rho is equal to R into A by L. From here only we can write. And if I put this formula here, it becomes kappa is equal to 1 by R into A into L. So here we can write 1 by R into L by A. Remember, this is the ratio between length and the cross-sectional area. L by A is known as cell constant, and obviously 1 by R we all know is written as G. So this is written as G, we all know, into this L by A is known as cell constant. So kappa is equal to G into cell constant. Regarding that also we have to solve various numericals. So these are the topics for today. We have seen what is conductivity, we have seen what is molar conductivity, we have seen the relationship between them, and we have seen various formulas, and this is a separate section altogether. Next day we are going to observe the Kohlrausch law and the numericals related to that. So carefully read this one, and these formulas are very, very important. Write them separately to remember them together.